everyone. My name is Akanksha. I teach physics to class 11th and 12th. I have completed my post-graduation in physics from Punjab University in the year 2019. Please stay connected with me for the next few minutes to understand how I teach. So our today's topic is cyclotron. We have taken this topic from class 12th physics. Now what is cyclotron? Cyclotron is a device which is used to accelerate the charged particle to a very high speed, or we can say that to a very high energy, as we know that kinetic energy is equal to half mv square. So basically it is a device which is used to accelerate the charged particle, and this accelerated charged particle is used for various purposes. Now a question always comes in our mind that why do we need a cyclotron? Why do we need to accelerate a charged particle to a very high speed or very high energy? The accelerated charged particle can be used for various purposes. For example, it is used to start a radioactive decay, to initiate a radioactive decay. Secondly, it can also be used to insert ions into the solid so that this solid can be used for various purposes by improving the electrical conductivity of the solid. Third thing is, this highly energetic particle can also be used to study various nuclear reactions. So before understanding the construction and working of cyclotron, let us first understand how the charged particle behave when it is present in electric field and when it is present in magnetic field. So here we have shown that we have a charged particle having charge plus q and mass m. M is the mass of the charged particle. Now this charged particle is present in an electric field. Now when a charged particle having positive charge is present in the electric field, it will always attract towards the negative charge. It will experiences an electric force which will basically try to attract the charged particle towards the negative charge, and the charged particle will start accelerating. Now, what would be the acceleration of the charged particle when it is present in the electric field? We know that when charged particle experience electric force, the force will be Q into E, that is the product of the electric field and the charge. Now, as per Newton's law of motion, force is equal to mass into acceleration. So, the acceleration of the charged particle comes out to be force upon mass. Force experienced by the charged particle is Q into E divided by M. So, this is the acceleration which the charged particle will experience when it is present in electric field. Now, let us understand the behavior of charged particle when it is entering into the region of magnetic field. Here we have considered a positive charge, and a positive charge is entering into a region of magnetic field. When the positive charge enters into magnetic field, it experiences certain kind of force, and this force will tends to change the direction of the charged particle, will change the direction or path of the charged particle. But always remember, magnetic field cannot change the velocity of the charged particle. It cannot accelerate the charged particle. Only electric field can change the velocity of the charged particle or to accelerate the charged particle, but magnetic field can only change the path of the charged particle, can change the direction of motion of the charged particle. Always remember that. The velocity of the charged particle in the magnetic field is always constant. It can only change the path. So, charged particle will experience a certain kind of force, and this force will tends to change the direction of the charged particle. This force is given by QV cross B, where Q is the magnitude of the charged particle, V is the velocity of the charged particle, and B is the magnitude of the magnetic field. Now, how can you find in which direction the charged particle will move after the magnetic force? The direction of force is given by right hand palm rule. Palm will represent the direction of force, your finger will represent the direction of magnetic field, and your thumb will represent the direction of motion of the charged particle. Now, in this case, as you can see that the direction of magnetic field is downward. So, finger will represent the direction of magnetic field. The direction of magnetic field is downward. Thumb will represent the direction of the charged particle, direction of motion of charged particle. So, this is the direction of magnetic field. Thumb represent the direction of motion of charged particle, as you can see here. So, your palm will represent the direction of force. So the charged particle here will experience its force towards the board. This is the direction of magnetic field. This is the direction of motion of positive charged particle. So it will experience its force towards the board. So this force will tend to change the direction of the motion of charged particle. It will not change the velocity. So the direction of the force is represented by right hand palm rule, and this is the magnitude of the force. Now there are three cases arises, or many such cases arises. As you can open this formula, V cross B is VB sin theta. So depending on this angle, the magnitude of force will also vary. Theta can be anything. Theta is basically the angle between the direction of motion of charged particle and the magnetic field. So this theta can be anything. We will consider three special cases to understand this more. Now, what will happen when the charged particle enters in the direction of magnetic field? Means the direction of charged particle and the direction of magnetic field is same. Second, when the charged particle enters in the opposite direction to that of magnetic field. And the third one is when the charged particle enters perpendicularly. Means magnetic field is downward and the charged particle is entering like this, making an angle of 90 degree. So what will be the effect of force which the charged particle will experience? As we know that the force is given by Q VB sin theta. Now, in that case, the angle between the direction of motion of charged particle and the magnetic field is same. That means here theta is equal to 0 degree. As you can see that velocity is in the same direction to that of magnetic field. So basically here theta is equal to 0 degree. We know that sin 0 is 0. So in that case, the charged particle will not experience any kind of force. It will go straight without even change in its velocity. We know that magnetic field cannot change the velocity, but also the charged particle will not change its direction. In the second case, when the charged particle enters the magnetic field in the opposite direction, here theta becomes equal to 180 degree. As you can see, magnetic field is in this direction and velocity is in this direction. So here theta is equal to 180 degree. We know that sin 180 degree is equal to 0. That means in this case also the charged particle will not experience any kind of force and it will go straight without even change in its direction, and we know that it cannot change the velocity also. Now in the third case, when the charged particle enter perpendicular, magnetic field is in the downward direction and the charged particle is entering like this. In that case, the angle between both is 90 degree and sin 90 is not equal to 0. Sin 90 is 1, which is maximum value of sin theta. So basically here velocity is like this and magnetic field is like this. So the force will be the resultant of these two. The magnitude of force will be resultant of this two. Because sin 90 is equal to 1, so the force will become QVB, and this is the maximum force the charged particle can experience. So basically, because of this force, the charged particle will start moving in a circular path like this. The charged particle will start moving in a circular path in the presence of downward magnetic field with a particular radius small r. And this radius is constant because this radius depends upon the velocity. Now, what will be the radius of this circular path when the charged particle is following a circular path because of the magnetic force? The radius of this circular path is mv by pq, where m is the mass of the charged particle, v is the velocity with which the charged particle is moving, and b is the magnitude of magnetic field, q is the magnitude of the charge of the charged particle. So it can be clearly seen that the radius depend upon the velocity and the velocity depend upon the radius. So whenever the velocity of the charged particle increases because of any reason, the radius of the circular path will also increase. For example, if you increase the velocity, the radius of the circular path will also increases. But magnetic field cannot change the velocity. Magnetic field can only change the direction. So if you apply electric field in addition to this magnetic field, only then the velocity will change, and if the velocity changes, then in the presence of magnetic field, the radius of the circular path which the charged particle is following will also change. But this can only be happen always remember when the charge particle enter perpendicularly. If the charge particle enters parallel or anti-parallel, then there will be no force. If the charge particle enters by making any angle theta, then the direction of charge particle will automatically change. This is the maximum force which the charge particle can experience when theta is equal to 90 degree. But zero force will be applied when the charge particle enters parallel or anti-parallel. Now let us understand the construction of cyclotron, how the cyclotron is made up of. Cyclotron is basically made up of two hollow semicircular metallic container called as Ds. This is one container named as D1 and this is another container named as D2. Now these both metallic containers are connected to a AC source which is high frequency and high voltage source. The voltage is around 10,000 volt and the frequency is very high, which is around 1 lakh to 10 lakh hertz. This frequency is very high and it is connected to a very high voltage source. Now this whole setup is placed between the two magnetic poles, North Pole and South Pole, in order to provide the magnetic field to the whole setup, and this AC source is used in order to provide the electric field to the whole setup. So basically in case of cyclotron, in between the gaps there is a charge present which we need to accelerate. So this whole setup contains electric and magnetic field, and the charge particle gets accelerated to a very high speed in the presence of electric field and in the presence of magnetic field because of these poles. Now a detector is provided across one of the circumference of metallic container. This detector is provided to deviate the highly accelerated charge particle from its path so that it will come out of the opening provided in one of the metallic container. Now let us understand the working of cyclotron, how the cyclotron will work and how the charge particle gets accelerated to a very high speed. As we know that the charge particle is present in the gap between the two metallic containers called Ds. Now, as we know that these two Ds are connected to a high frequency oscillator having very high voltage. Let us suppose at a particular time t, the D1 is at positive charge and the D2 is at negative charge. Now, when the charge particle which we need to accelerate to a very high speed, when this charge particle is present in the gap, suppose this charge particle is positively charged, so it will attract towards the D2. Now we know that this is a metallic container, so when it enters inside the D2, because this is a metallic hollow container, we know that electric field inside the hollow container is 0. But inside the hollow metallic container, it will experience the magnetic field. The direction of magnetic field is downward and the direction of electric field is from left to right. Now, when the charge particle was present in the gap, it will experience the electric field and magnetic field both. But when the charge particle enters into the D2, it will only experience the magnetic field and the electric field inside this hollow container will be 0. Now, we know that when magnetic field is in the downward direction and the charge particle enters perpendicular to it, magnetic field is in the downward direction and the charge particle enters to it in this direction. So basically they are making an angle of 90 degree. In that case, we have discussed earlier, when the charge particle enters in the region of magnetic field perpendicular to the direction of magnetic field, it will follow the circular path having constant velocity. So basically inside the container, the charge particle will start moving in a circular path, right? The charge particle will start moving in a circular path, but the velocity remains constant inside the container because magnetic field can only change the path of the charge particle but cannot change the velocity. Only electric field can change the velocity of the charge particle. So basically this charge particle will start moving in a circular path. Now, when the charge particle again comes outside and present in the gap between the D, again the high frequency oscillator changes the polarity of the Ds. The frequency of the oscillator is set in such a way when the charged particle enters in the gap, then only the polarity of the D's will changes. So basically at that time, the polarity of the D will change when the charged particle enters the gap again. Now the D1 will becomes negatively charged and the D2 becomes positively charged. When the charged particle enters in between the gaps, at that time it will again experience electric field and magnetic field both. Now we know that electric field will accelerate the charged particle. So when the charged particle enters in the region, it will accelerate, and then because of the negative charge, it will attract towards the D1 and enters into the D1. Now, as we have discussed earlier, when the charged particle is present in the magnetic field, so basically the magnetic field changes the direction of the charged particle and the charged particle starts moving in a circular path. Now, we have already discussed that the radius of that circular path will be mv by pq. Now, there is one question that will the radius of the circular path which the charged particle follows in the d2 will be same as the radius of circular path will the charged particle will follow in the d1? The answer is no, because when the charged particle enters into D2, the velocity of the charged particle was not that much high, but after the charged particle comes out of the BD2, at that time electric field basically accelerate the charged particle. Now because of the acceleration, because of increase in speed, as we know that from this formula, if velocity of the particle increases, so radius of the circular path which the charged particle will follow will also be increased. So basically at that time in the D1, the charged particle will follow the circular path with much greater radius, because in this case in the D1 the velocity of the charged particle increases because of the electric field. Now again, when the charged particle comes out of the D1 and enters in the gap, then again the polarity of the oscillator changes, and now the D2 becomes negatively charged and D1 becomes positively charged. Again the polarity changes. Now the charged particle will again enters the D2. At that time the velocity again increases as the previous. So basically the radius of the circular path will again increases. So in this way the charged particle will start following the circular path and a stage will come when the charged particle acquires a very high velocity and it reaches along the circumference of one of the metallic D, and it strikes with the detector which is very close to the circumference of the D. This detector will deviate the charged particle and the charged particle will come out of the opening and will be used for several purposes, and the velocity of this charged particle is very high and energy of this charged particle is very high. So in this process we can say that with the help of electric field and with the help of magnetic field, we are able to accelerate the charged particle to a desired velocity and to a desired energy which we required. So in this way, because of the help of magnetic field and electric field, the acceleration is possible. Now let us calculate the velocity of the highly energetic charged particle which comes out of the D. So in order to find the velocity of that highly energetic charged particle in magnitudes, we know that when the charged particle came out of the metallic container with a very high velocity, the radius of the circular path which the charged particle follows in the end is approximately very close to the radius of the D. Let us suppose the radius of D is equal to capital R. Radius of the metallic container is equal to capital R. Now we know that when the charged particle came out of the metallic container, it follows the circular path having radius approximately equal to the radius of the D. So we know that the radius of circular path is mv by pq. We know that the radius is approximately equal to the radius of the D, radius of the circular path, because when the charged particle came out of the D, it follows the radius approximately equal to the radius of the D. So basically here we can write capital R. So the velocity of the charged particle comes out to be capital R BQ divided by M. We know the value of the mass of the charged particle. We know the radius of the metallic container. We know what is the amount of magnetic field we are applying, and we know the charge of the magnitude of charge of the charged particle. So using this formula, we can calculate in magnitudes what is the exact velocity of the charged particle, highly energetic charged particle, which comes out of the D. Or we can also adjust the velocity as our requirement, what kind of velocity, what is the magnitude of velocity we required. So we can also adjust the velocity with the help of adjusting the magnetic field and by also adjusting the radius of the D's. So basically, time period is the time taken by the charged particle to cover one circle. Which is what is the time taken by the charged particle to cover the one circular path? Time period can be calculated as time is equal to distance upon velocity. Now we know that velocity is equal to PQ capital R by M. Here we are calculating maximum time period. What do you mean by maximum time period? We are taking the velocity with maximum radius. So basically we are calculating the maximum time period which the charged particle can take to cover the circular path. Time period can be less than this but cannot be more than this. So we are calculating the maximum time period because we are taking the maximum radius. As you can see that there are many circular paths, but we are taking the maximum radius, that is the radius of the D. Radius cannot be more than capital R. So we are taking the maximum radius, we are taking the maximum velocity. We are calculating basically the maximum velocity. So basically we are calculating the time period, maximum time period which the charged particle take to cover a circular path. So basically time period is equal to, now what is the distance? Distance is basically 2 pi r, which is the circumference of the circular path, 2 pi capital R divided by, put the value of velocity, BQ capital R divided by M. So here your time period comes out to be 2 pi M by BQ. So this is the time taken by the charged particle to cover a circular path inside the metallic container. Now we have to calculate the frequency of cyclotron, or we can say that the frequency of the AC oscillator which we have used to connect the D1 and D2. Let us understand one basic and simple thing. We know that we have used an AC source. So when positive half cycle of AC source was used, the D1 becomes positively charged and D2 becomes negatively charged. In that case, charged particle which was initially present in the gap attracts towards D2 and follows semicircular path during the time of positive half cycle. Now, when the charged particle again enters in the gap after covering this semicircular path, the polarity changes, means negative half cycle of the AC source was used. Means D1 becomes negatively charged and D2 becomes positively charged. During the time period of this negative half cycle, the charged particle covered the semicircular path in the D1. In this way, the charged particle follows the complete circular path. We can say that the time taken by the charged particle to cover this complete circular path is equal to the time period of the AC source cycle. So in that way, we can also say that the frequency of the AC source oscillator is equal to the frequency of the charged particle, the frequency with which the charged particle is covering the circular path. We know that we have already calculated the time period of the circular path which the charged particle has covered is PQ 2 pi M by BQ. Now we know that frequency is equal to 1 upon time period. So frequency comes out to be BQ by 2 pi M. So basically this is the frequency of the AC oscillator, or we can say that this is the frequency of the cyclotron. Now let us discuss the limitations of the cyclotron, where the cyclotron cannot be used. As in the beginning, I have told that cyclotron is a device which is used to accelerate the charged particle. And in the working and construction, you clearly understood that cyclotron cannot be used to accelerate the neutral particle, because initially when the charged particle is placed in the gap between the D's, it attract towards the d2 because of the positive charge, because of its positive charge. If the charge particle was neutral, then it will not attract towards the d2, because only charge particle can attract towards the opposite charge. So basically this process will not start if the charge particle was not used, and rather than this we use neutral particle. So basically we cannot use this process, we cannot use this apparatus to accelerate the neutral particle. We have to use the charge particle to accelerate if we want to use cyclotron. So the first limitation is cannot be used for neutral particles. So my question is, can you use the cyclotron apparatus for neutron? No, you cannot use this apparatus to accelerate neutron, because neutrons are neutral particle. You can use this to accelerate proton, but you cannot use this to accelerate neutrons, because neutrons are neutral particles. So neutral particle cannot be used here. Now my question is, can you accelerate electron with the help of cyclotron? You might be thinking yes, because electron is of negative charge, negatively charged particle can be accelerated. But my answer is no. Electron cannot be accelerated by cyclotron. Why electron cannot be accelerated? It has negative charge, so it can be used, but no, electron cannot be used. Why electron cannot be used? I told you that frequency of the oscillator is pq by 2 pi m. Now you know that electron is a very light particle. The mass of the electron is very, very less. So when the electron is accelerated in the cyclotron, the velocity of the electron becomes easily relative to the velocity of light. In the relativistic concept, when the velocity of particle becomes very close to the velocity of light, the mass also affected. Electron is very light particle, so it can easily achieve the relative velocity because of the acceleration process. So that is why the mass of the electron will also changes. If the mass changes, so the frequency will also affected. If the frequency affected, so the frequency will not match. Frequency will not match, the time period will not match the time period of the AC oscillator. The frequency of the AC oscillator will not match with the frequency of the charged particle. So in that case, again the polarity will not change at time. If the polarity will not change at time, so the process will not work. So basically electron can also not be used in the process of in this apparatus. We cannot accelerate electron with the help of cyclotron, because mass of the electron will suffer. If the mass will change, the frequency will also change. So these are the two limitations of cyclotron. You cannot accelerate neutron with the help of cyclotron because these are neutral particle, and also you cannot accelerate electron with the help of cyclotron. Thank you so much for watching the video. I hope you liked my lecture and understood the concept.